It depends on, I get the nervous energy, I finish the whole thing in 5 minutes. When did you see me speak? No, I did not speak. I was supposed to not speak and I finished my job. No. Yeah, but like 3 words and then I got off the stage. You didn't even hear me. August, March, I planned it. Like, no, he can't be joking. No, I'm just scared. But no. Oh, yeah. But it came from the house. Did you get a free song? Did you shiver? Free song. It's a shiver of excitement when I see, or of pride when I see the. I'll try today. I'll try hard. We'll see how many people run away. Oh, that's why you're there. Oh, look at that. Worse. Come follow me. Right. Step out and block the door. Hey, everyone. Thank you for coming. I will be giving a shortish lecture. For those of you who haven't grabbed lunch, there's lunch outside, so grab lunch. It makes the experience of listening to my talk much, much better. By the way, the person who you see outside and this person are totally different people. The person outside seems to be smiling. I don't smile. The person outside seems reasonably dressed. This is what you get. But anyway, having said that, I'm going to launch into my talk. It's called Traffic Engineering Redux. And on the face of it, it's a routing area geeky talk. But there's actually 2 themes that go through it. One is lessons you can get from philosophers and apply them to your routing protocols. And the second is just a personal story of mine, a journey that I took over a long time. So I'm going to try to at least have some of those come through. But being a geek, I might just go off and just do the geeky thing. So if you guys can somehow say, hey, what about the story? What about the philosophers? That would help, but I'll try to do that myself. Okay, so redux. When MPLS was introduced, one of the big things that people wanted to talk about was traffic engineering. And this was codified, the requirements for TE were codified in RFC 2702. And they talked about MPLS, requirements for traffic engineering over MPLS. One of my first tasks at Juniper as a routing protocol person was to implement some of this. So this was, I've had a close relationship with traffic engineering for 27 years. A few things have changed, and some of them are important, but in a lot of ways, this has remained very much the way it was. So there's a feature called auto bandwidth. So in MPLS traffic engineering, you say I want a bandwidth of 2 gig between these 2 points, and it's very hard to find a number. So auto bandwidth allows you to give a range, and things change. So that's much more adaptive, and so that was nice. But fundamentally, things have remained pretty much the same. So I want to come back to the subject because I think we've learned a lot in the meantime. And one of the things that occurred to me is that there seems to be this dichotomy, and I'll talk to that in a second, between equal cost multipath or just simple load balancing and traffic engineering. So I think that that's a false dichotomy, and so I'm going to try to explain to you by explaining in some more detail why we do ECMP and why we do traffic engineering, that dichotomy might actually be resolved. Okay. So yeah, this is what I said. ECMP, equal cost multipath, load balancing, a bunch of different names. If I am starting at a node and I want to get to a different node, multiple paths across the network to get there, they all have to be the same cost, and I'll explain why that is in a little while. This is easy. It's very powerful. It's something that Dijkstra came up with for a different reason, but it turns out to be very powerful in networking. One big thing is it doesn't need signaling. It doesn't need tunnels. Traffic engineering, on the other hand, is not quite as easy, and in some senses more powerful, but it requires signaling. It requires tunnels. And so you had this choice in your network. Am I going to go with an ECMP style network, or am I going to go with traffic engineering? And for those of you who've read Hegel, or you know that this is a great starting point for what he calls Aufheben, which basically means you have two concepts that seem to cancel each other, but at the same time they can reinforce each other. So if you actually got into Hegelian dialectics, you would say, this is a great opportunity. So hold that thought. Okay, so equal cost multipath. You have a node N. You have a packet arriving at this node. You're doing simple destination-based forwarding. And so you say, I can take any of these paths. They all reach the ultimate destination with the same cost, with the same path length. So when you do that, you say, okay, I'm going to pick any of these. I'm going to, toss a roll a die or toss a coin or do something and decide which one of these I want to pick to forward this packet. So can this cause routing loops? I mean, I'm making this random decision. Can really bad things happen? Well, actually, what happens is if every node has the same picture of the IGP, and that's of the topology, and that's what IGPs do, they all run Dijkstra's shortest path algorithm. That's guaranteed not to cause routing loops in the network. Now, if there are transients, stuff can happen, but in a steady state, everyone knows what the topology is. They all run Dijkstra, and life is good. You don't have loops. So Dijkstra basically came up with this algorithm while sipping coffee outside a little mall or some shopping center, because he wanted to know how would I find the shortest path to some destination. So from his point of view, this was a really nice, clean algorithm. It was, a solution to a graph algorithm. It was very efficient. It was not just simple to implement, but it was also simple to prove. So the proof of this is like undergraduate exercise. And so, you had a powerful algorithm that solves a real problem. It solves it very efficiently, very much in polynomial time, and it's provably correct. And the funny thing is that it uses the principle of, greedy algorithm. So you just pick the node that has the shortest length and say, let me continue with that, and you keep going. So greediness works in this case. Not every algorithm could be done this way. So he was thinking of it as a way for solving this graph theoretical problem. But if you look at it from a networking point of view, every node in the network can say, I want to compute the shortest path to this destination. They'll all come up with the same answer or close enough, because if they say, let's all find all shortest paths, fine. If they all find one shortest path, fine. The point is that if you're forwarding packets based on this computation, you're not going to cause a loop. So it turns out to be really interesting for forwarding algorithms. So let's look at why this is interesting. So you have the same junction, and you have a traffic surge, which you were expecting maybe 2 gig, and suddenly it's surged up to 5 gig. What's going to happen is, since you have 3 outgoing next hops, you can spread that surge across those 3 next hops. So that's really good. Most of the time. That means no one link would get over congested. So if you had a single next hop, you don't have a choice. You're going to push the traffic there, and then you could have congestion. But here you can spread it out. The other thing that happens is, the other thing that happens is, if you had a link fail, you still have 2 more next hops that work. So you just say, okay, I'm going to rebalance how I send traffic. And so instead of sending it across all 3 links, I'll just send it over 2 links. So it gives you protection without working hard at all. It gives you this management of traffic surges. So it's all very cool. There are some downsides. One question you can ask is, if I'm doing load balancing, what ratios should I use to balance the traffic across these different links? And so you could say, I have 3 links, I'm going to put 1/3 on each. That's kind of a broken algorithm, especially if you see in front of you 2 of the links are 10 gig and 1 link is 1 gig. So at least in front of you, you can say, I know the speeds of these links, so I'll put 20 to 1 in the case I just mentioned. Okay, you're doing better. But the problem is that 20, the topmost link, might have next to it, the next hop for that guy might only be 1 gig. So you could put 20 there, but you're just going to way over congest the next link. So if you're looking just locally at what's happening at my node and my immediate neighbors, you're not going to make good decisions. So yes, you can load balance, but the actual load balancing it's going to be rather naive. If you had just a single link, single next hop, and it broke, what do? Traffic came in, you have to send it back. Well, You're looping now. So yes, it does protection when you have multiple next hops, but if you have a single next hop, it's not going to help you. People have come up with answers to this. It's way more complicated than the initial Dijkstra algorithm. So it has good things, but it doesn't solve everything. ECMP is still a really good answer. Many people run their networks this way, and that works. But you just have to be aware that there are a few things that could trip you up, and you can address them by making sure that you don't have a single link anywhere. In other words, if I am trying to go from A to B, there are multiple paths available. A flow network that's typically used in, say, machine learning clusters or data centers is the epitome of ECMP networks. So it's almost like you're going to engineer the network. So we're going to talk about traffic engineering, but here you're engineering the network for your application. So you essentially say, if you think of these nodes on the left as super spines, the ones in the middle as spine nodes, and the ones on the right as leaves. The links between the super spines and the spines are going to be exactly the same fiber length, same bandwidth, same everything. The links between the spines and the leaves, again, the same thing. They don't have to be the same as the previous, but among themselves, they're all going to be the same. So you've engineered the network for maximal load balancing. So this works really nicely. And so that's basically what I just said. So in this kind of network, you have absolute ECMP. Every hop you can do lots of ECMP, and you can use this network really, really efficiently. There's a catch, and we'll come back to that in a second. And to understand that catch, we're going to call upon our dear friend Jean-Paul. So Jean-Paul, whoops, he's shy. He basically said, existentialism means you must choose. So his expansion of ECMP would probably be, if he was a network engineer, existentialist choice must prevail. What does that mean? First thing is, if you're living in bad faith, and he put it as mal foi or mauvaise foi or something like that, you must choose at the moment. You cannot say, my dad did it this way, my teacher taught me this way. You cannot make those kinds of excuses. In the moment, you got to make choices. So you cannot abdicate your choice. However, when we do ECMP, we do flow-aware load balancing. What that means is when you get the first packet of a flow, you do a hash and say, okay, that packet is going to go on this link. You get the next packet in the flow, you're going to put it on the same link. It's like, what happened to choice? No, I am. Those excuses are what makes you live in bad faith. So, Sarth would be very unhappy if we did flow-aware load balancing. Well, what does that mean for us today? If this works. So yeah, let's just look at the junction. So a packet comes in to node N. If you say, I was told by traffic engineering to go on this link, Sarth would kind of frown at you. Yeah, I'm going to say something nice about traffic engineering eventually, but right now, the way it's happening, it's not going to work for Sarth. If you say, I sent the packet in a different packet in the same flow this way, so this packet will also go that way. Again, you're not living to your full freedom. So what you really want to do is to say, every time a packet comes in, I'm going to make a free choice and send it among any of these links. Does that work? This is called packet spraying or per packet load balancing. If you want fancier names for it, It's a disaggregated schedule fabric, and that's what Meta calls it. The Ultra Ethernet Consortium is working on this. Fungible, a company that got acquired by Microsoft, built DPUs that did this. Way back when, for those of you with a long history with Juniper, we built a product called the M160 that did this, and we got killed. So the problem with this is, Sarth is going to be happy. Your apps are not going to be happy. So do not do this unless you have a way of putting packets back in order at the other end of it. So somewhere you have to say, my packets came in a certain order. I'm going to put them back in that order. So in the case of, and the formatting here has gone really bonkers, but in the case of DSF or UEC, all these different approaches to this, they have a sort of a bookended solution where you grab the packet, put a sequence number on it. At the far end, you then buffer them, put them back in order, and then push them back to the application. So if you can do that, this is good. If you do this, though, the efficiency of your load balancing is very close to 100%. Whereas if you do per flow-aware load balancing, it depends very much on how the flows are. And so you have this notion of elephant flows and mice flows, and your load balancing can be really ineffective. Okay. If you had a machine learning cluster like this, you could look, I don't know if this, yeah. So you've got this is going to be a bit tricky. You've got your machine learning workload back here. You've got these GPU NICs connecting into your CLO network. And so you could say, packets that I send here, I'm just going to spray them. I'm going to timestamp them. I'm going to not timestamp them. I'm going to put sequence numbers on them. I'm going to let them spray across the network. I'm going to use my network fully. And when they come out the other end, I'm going to put them back in order before I give them back to the algorithm that I'm running. If you do this, your clusters become really, really efficient. At least this side of the cluster, the networking part of your cluster becomes very, very efficient. If you don't do this and you get a big elephant flow, you could be underutilizing your resources. Okay, so now let's go to traditional traffic engineering. Basically here, what you do is you define constraints. These are the kind of paths or links or nodes that I want my path to go over. I define a source, I define a destination. So here it's A and Z. And then say, find me a feasible path from A to Z that satisfies the constraints. So for example, you say, I want a 20 gig path. I want to go over green links and avoid some other links, insecure links and whatever. The definition of green and insecure is up to the operator. So you do this, and then you compute the path, and you say, oh, you go from A, and over some hops you get to N, over some more hops you get to Z. So N has no idea what the constraints were. So for example, N doesn't know that it's supposed to avoid insecure links, whatever those are. So N cannot just say, I'll forward packets on my own. So N has to be told, this is your next hop. This is how you're going to send packets. And so when you do that, you're going to have signaling where A tells N, this is the situation. This is what's happening. So don't just decide on your own what to do. RFC 2702, the requirements of traffic engineering, basically said, implicitly talks only about paths. It doesn't talk about having multiple paths. So from then, 1998, our heads have been filled with, it needs to be a path. RFC 3209 that gave us an implementation of this created a single path. So again, it's in our, it's deeply instilled in us that it needs to be a single path. Like I said, Jean-Paul would not be happy. So the IGP extensions distribute properties that allow you to do these constraints and computations. Okay, so if a link fails, what happens? Well, let's say I have this, the next hop for N is M, and the link between N and M failed. Well, I could compute a different path to something downstream, and that would again be a signal path. It doesn't have to go over a shortest path. Once it's signaled, I can do it any way I want. So I just say, I need traffic that goes from N that used to go to M to take a different path to go a little further down the line so that it eventually will get to the egress. So the point is, once you're off this regime of I must follow shortest path, you are in the regime of I'm going to signal the path to you. You can deal with errors much more easily because you're going to actually compute those paths. Now, this might be distasteful to some because you have to do signaling. There are other things about it, but it does mean that protection becomes much, much easier. So TE has seen some decent deployment. So the ability to set up protection paths has been a big driver initially, but later people started using bandwidth, and then when we did the auto bandwidth, it became much easier. So bandwidth reservations, especially with this auto bandwidth. One complaint about this was that you have state in the network. And if you have state in the network, it makes it potentially harder to scale and do various things. But that same state allows you to get a much clearer picture of where the traffic is flowing in the network, how much traffic you have, and so on. So state in the network is not all bad. So on the flip side, you have the people who say, let's just throw bandwidth at the problem. And working for a vendor, we're more than happy to sell you more 100 gig interfaces, 400 gig interfaces, and so on. But people are now coming back and saying, yeah, we can't keep doing that. So what is the alternative? If I don't want to manage my bandwidth, then I just have to keep buying more and more higher and higher capacity interfaces, keep growing my network. But if I want to use the network I have more efficiently, then I have to be able to place it. So this is kind of the dichotomy that they face. There are concerns about state. I'm not saying that state is for free. But I think the problem is not that there is state. The problem is for us to control the state and make it useful. But I think the biggest thing is that there are those who say, look, there's a powerful technique called ECMP, and you're forcing me away from that. You're not giving me, you're saying either do ECMP or do traffic engineering. I want both. For those people, yeah, this talk is for you. So this notion of multi-path traffic engineering is this Hegelian approach that you've got the thesis, which is ECMP, you've got the antithesis, which is traffic engineering. And instead of saying, oh, I have to do one or the other, and how do I deal with it? The whole thing that you're supposed to do to reach this higher plane of existence, this is Hegel's words, not mine, is to find the synthesis that says, I can do both. And so what multipath TE tries to do is to do both. So going back to this network, I have A, my ingress, my source. I have Z, my destination. I have this node in the middle. And I say, I'm going to do the same thing I had before, define constraints, but don't find one path. Find all shortest paths from A to Z that meet the constraints. So you'll end up with something a lot better eventually, maybe. So it says find a path. Why a path? So let's find all paths. So RFC 2702 implicitly assumes a single path, and 3209 signals a single path. So put those aside. They're not going to help us. Since you're signaling, you can find a different signaling algorithm that allow you to signal multiple paths. Since you're signaling anyway, you can also ask why only shortest paths. So why not find all paths from A to B that are loop-free, of course. And given that, because you're signaling, you can do that. You can then ask why go to a single egress. So what I'm trying to do is to go back to 2702 and say, everything you wrote down there, all the assumptions you made, I'm going to call them out and ask why, ask why, ask why. And this is part of the personal journey that I'm going to talk about at the end, if I remember, if I ever get there, which is, well, I'll get there. So the T paradigm was start at the ingress, go to the egress, look for these constraints. When you satisfy them, find a single path that gets you there. The first question is why one path? So find all paths. Second question is why shortest paths? So okay, let's use all paths. And the third is why single egress? And there's actually very good use cases where you might want a second egress. If Y and Z are both peering with the same AS on the other side, they might get the same routes. And once you do IBGP path selection, minus the last step, which is tie breaking based on loopback addresses, A could say, I could send traffic to either of those. So rather than A trying to pick randomly which one he wants to send it to, A could say, give me a DAG, a directed acyclic graph, that starts at A, goes to Y and Z. I'm going to put my traffic on that DAG, and it might show up at Y, it might show up at Z. Either way, it's good. So this whole idea that you had a path, and then you had a path that well, a set of paths that were shortest paths. You said not even that. They all have to be feasible because your constraints are not negotiable. But if you say from A to Z, I have many paths, and then you say Y is equivalent, so then you might say from A to Y or Z, give me all the paths. You're getting to the place where you're coming back to having a high degree, not the same degree of ECMP as you would without constraints, but a high degree of ECMP. You can also ask why a single egress. I haven't found a really nice use case for it, but maybe. Okay, so this is what you might end up with. You have this network that starts at A and ends up in YZ, and you have all these nodes in between, and you have almost everywhere, you have at least two next hops. The one place you don't have two next hops is C. C to D, and just assume all the traffic is moving left to right. So C to D, you have a single link, single next hop. And so if the CD link were to break, you'd have trouble. So most of the time, you don't have to build protection paths because your protection path is the other links you have. But in the case of C to D, you do have to build a protection path because there is no other link. But since you're signaling and since you're not working with shortest paths, this works. Okay, I actually can't read. I maybe should have used better colors, but whatever. So if you go back to the machine learning cluster, this, like I said, this is the epitome of ECMP. Well, if you're you've got this network that's engineered for ECMP. Can traffic engineering possibly help this? Well, if you're running a gigantic, large language model on this, then you want to use the entire cluster for one thing. Leave it as is. Oops, I went too far. Oops, I'm just going to try to get back to where I was. There's a huge lag between this and this. I think it goes from here to San Francisco and back. So here's your machine learning cluster. And if you are doing one gigantic LLM, large language model, you want to use the entire cluster for that. But if you're doing a bunch of smaller jobs, let's say you have just two sets of jobs, you might want to break the cluster up into two logical clusters and say the servers and GPUs connected to L1 and L2 are working on one inferencing model, and the servers that are working on connected to L3 and L4 are working on a different model. Then you want to say, I want to segregate the traffic so that I'm using my network efficiently for each of these clusters. So actually, the idea of bringing traffic engineering to a network that is engineered for ECMP might really make sense. And I think that people are actually working on this. So this partitioning of a big cluster, which sometimes you use as a big cluster because you have a really, really big job, to a bunch of smaller clusters using TE techniques so that you can get multiple jobs done in parallel, seems to be an interesting idea. Okay. Okay, so the basic idea then is I don't have to think of ECMP or traffic engineering as this. I have to pick one, and if I pick one, it gives me a certain ethos in how I build my network. It also gives me a certain characteristic that my network will have because of that. You can actually do both. And so this is this whole thing where you go back to you can meaningfully add multipath to traffic engineering. You can meaningfully add traffic engineering to a flow network, and so to an ECMP style network. And so you're basically saying, I can get past this thesis and antithesis and get to the next level where I actually have multipath TE. And so that would lead you to, here's a very different way of building my network. I would still need signaling because anything with TE needs signaling, but I'm not giving up ECMP in doing that. And to go further, the choice between per packet load balancing or per flow load balancing is orthogonal to this. So you could say, I'm going to build a network for multipath TE, and for this kind of traffic, I'm going to do per packet, and for this kind of traffic, I'm going to do per flow. So you are actually in a place where you can mix and match all of these things together. So that makes your network that much more powerful. The other thing I want to say is that with the lessons that we've learned from trying to implement traffic engineering the way we did, where when you're done, you have a single path and you have a bunch of state associated with it. Then you have another path and you have a bunch of state associated with it. If you actually create what I like to call a DAG, a directed acyclic graph that captures all of these paths together, then you could have a much more scalable approach to state. So the amount of state you have will be much less. And I think there are other things we can do in the protocol to make the state, to make the protocol scale better, to make the churn in the protocol less. So there's a number of things that not only do we break this bind between ECMP versus TE, you also rethink the protocol with the lessons learned in the last 25, 27 years to say, I can do this much better. So I'm not here to sell TE to you. If I sold it by accident, great. What I'm here to do is really make you think about TE. So that's my high order goal. Having said that, I also want to say one more thing. The fonts have all gone crazy, so this has all gone a bit wonky. But when I went to the US, I went to the US to do a PhD. And I had an advisor, Edelman of RSA fame. But there was a father figure for PhD students. And one of the things he tried to drill into us is, so he was a Fletcher Jones professor of computer science at USC, University of Southern California. And he used to say, you can respect people, but that does not mean you should be in awe of them. Always question, always challenge what's been told. The passed down wisdom, of the elders, the passed down wisdom is nothing sacrosanct. You can change things. So the last thing, which even you can't see, is have the courage to rethink. So these were the things that he tried to drill into us. And so if I think back to this whole thing, 27 years ago, I was given a task, go implement this. And there were these people that, I knew nothing about networking or traffic engineering or IGPs or anything, actually. And I was given this task, and I said, I'll do it. And I think I did a decent job. And it's been there. It's been there for 27 years. And while it's been there for 27 years, yes, at some point I woke up and said, is this the only way it can be done? Is this the only way that one should think about traffic engineering? So basically, going back to what Seymour said, it's, yes, these guys did pass down this wisdom, but you're allowed to challenge it. And so for me, it's like, okay, and that's why all these questions come. Why does it have to be a single path? Why does it have to be a shortest path? Why does it have to be a single ingress? Why did it have to be a single egress? And so if you ask those questions, then at least you have a hope of doing something different. And maybe this is different and better, maybe not, I don't know. But for me, it's like, oh, finally, Seymour is gonna say, it only took you 27 years, but you did listen to me. And that makes me happy, and maybe it makes him happy. That's basically all I had. Questions?
Hi, Kireeti. Dave Oran. In the spirit of what you just said, why only equal cost paths?
Say again?
In the spirit of what you just said, why only equal cost paths? Why not unequal cost paths with proportional traffic splitting?
Yes, excellent question. And so read the draft, but it's there. But I'm glad we're like on the same wavelength. Yeah. And that's the nice thing, when you take one brick off the Berlin Wall, next thing you know, the wall is gone. So, but if everyone says, no, the wall is there, it's always been there, it's there to stay, it doesn't go anywhere. But take the one brick out, then the next, then the next, and then Hegel says, thank you, guys. Any other questions?
Thomas Eckert. Found any poor students to do simulations to simply say here, example recipe A, results my new recipe B, results tastes much better? Simulation, simulation, so
yeah,
that you don't have
yes.
to go and deploy 200 Juniper routers. They're so heavy, and it takes time.
Yeah,
so.
yeah. So right now, I've started writing code after 10 years, and I've gotten to the point where I can do the computations. The next step I want to do is to compare state between creating, 100 point-to-point LSPs or single-path LSPs versus a DAG that encompasses all that, and then compare what the fib state would be, what the control plane state would be, at least as an initial starting point. So that is on my list of things to do whenever I get this thing done. But I'm with you. We will have simulation. We'll have some idea of how this improves things. Yes. Rudiger.
Rüdiger Volk. Well, okay. First, a remark. Why starting from the one ingress, one out, egress, and one path? Oh, that's so bell-headed.
You're not wrong. You're not wrong.
And kind of coming more from the net-headed side, kind of when I had to do things, actually I figured that my task was not to deal with a single flow being mapped onto the network, but a network and a load distributed around all of the edge,
yeah,
and engineer the damn network so that it optimally uses the available resources for the traffic load offered.
Yes.
Is there any way to do this Hegelian or Sartrean or whatever?
So let me answer your first question. That's the easy one. Back when I was given my task of doing traffic engineering, the people who wrote RFC 2702 were UUNet, if you remember UUNet, Unix to Unix networking. And they ran their network, an IP network, as an overlay over ATM. So you're totally right when you said bellhead. And so it is single ingress, yeah. I mean, like, I was not questioning what I was asked to do. I was just trying to do what I was supposed to do. Took me 27 years.
Yeah, well, first of all, actually, I started out in USUP as well. And I'm surprised that from that you got into ATM and then so on. But yes, well, okay, we know. What was the name of MPLS before it was made agnostic of ATM?
Tag switching, cell switching, various things, yes. So, I mean, I get your point, but yeah, so I get your point. And like I said, there are people who do not want to do TE. There are people who do not want to do signaling. The beauty of what Dijkstra said is really there. I mean, I see the elegance in his solution. But if you do want to say, do not send traffic on this link for this particular type of traffic, or do not send traffic outside of my country because I have sensitive information running on that, then just using shortest path forwarding and IGP forwarding is not going to cut it. Tortoise.
Yeah, sorry, if nobody else here, I'm happy to monopolize this mic.
Yeah.
So I've been beaten over the head with the ambiguity of the term traffic engineering in some of the work, and maybe I'm still actually not clear here which more precise term may apply to this, because I've seen a lot of people confused about it. And most of the use cases I've seen is what I would rather call capacity engineering, right? Getting more out of a crazy topology by using all the path to the best of their abilities.
Right.
To some extent, there is something like maybe completion time engineering, that individual flows are also faster. But the classical traffic engineering, well, I think Adrian isn't in the room. He owns the RFC with the 400 pages of what it could mean. But classical, traffic engineering might probably be, well, in the world I'm living, like .NET, more hard guarantees of latency, throughput, and that stuff, which I think that isn't doing. So maybe one suggestion would be to get away from traffic engineering as you know it, as kind of the specific technology underneath it that you're using, over to, representing what it gives for the traffic or the network, because what you were just saying implementation-wise also seems more like engineering, the scalability of state in the network. So maybe, that helps to better sell the idea from low level where you may be to, the operators that you want to sell it to.
Right. No. Excellent suggestions. And right now, where the draft is, it's not. It hasn't made a lot of choices in terms of, you have to use this protocol or you have to use this tunnels, or, I mean, fundamentally, if you're not doing shortest path routing, you can't use Dijkstra. You have to have tunnels, you have to have signaling. But apart from that, there's not been any like hard choices. So, and so that does leave it open to looking at other applications of traffic engineering or other views of traffic engineering, and say, okay, we can bring that into this, or maybe it doesn't fit. But I'm hoping it would fit. So it's a good suggestion. Boris.
Yeah, for the multipacity, how do you control the state within the network device? And the second question is to achieve the desired effect, would you like to, do you need to resolve the source within the network?
So what was the first question again?
How you control the network state within the device? I think you have mentioned in your presentation.
Yeah. So with traffic engineering, you're going to have state. And so we're taking a different approach to the type of state you want to put in the network. And we're also taking the approach that you make the state as, down to the minimum that you can. And you want that state to be useful, not just to forward packets, but for doing other things. Like maybe this is a point where if I measure the traffic going through this particular junction, I get some insights into what is happening in my traffic or where the bottlenecks are. So there's going to be state, and people who say I can run a network that's not that is stateless, they're just fooling themselves, because networks have state. The question is the state useful? Is the state minimal for the task it's doing? And is the state allowing you new features that you couldn't do otherwise? So that's our approach to state. Yeah,
because in our network, there are some reasons why the traditional MPL traffic engineer didn't deploy widely. I think the challenge may be from the network state, and you must change the state based on the network conditions. It will be very challenging. So I think some similar situation will be faced for the MPTE. So I think from your protocol design, you think you should consider this in advance.
Okay, thank you.
Kireeti, Boris Kasanov. So it's not a question, just maybe a comment or suggestion. When you would make these calculations, comparisons, it would be, I think, correct and good compare with our, let's say, algorithms which we have in graph theory, because we should rely on some algorithm when we make this decision,
yes.
P next hop and next hop, right? So
right. Yeah, I mean, the thing about many of these things is the cost of doing Dijkstra Doesn't matter if you're starting at a node and going to another node and say, find me one path, or you say find all paths. The asymptotic cost is the same. And if you're doing Dijkstra with link constraints, that can be done just by looking at the link. Again, so that's what we call constraint shortest path first, CSPF. It's also the same. So, and in fact, even if you do this non-shortest paths, the time is the same. I mean, we don't count if it is twice as much, but it's not order of magnitude higher. So all of those paths are easy. The comparisons I want to do is to say, I'm here, I'm trying to go here. The old TE said make one path. Okay, we know one path is too little. So what if I make 100 paths? And how much forwarding state do I have to install based on that? Or if I create a DAG, how much a directed acyclic graph, how much forwarding state do I have to put? So I want to compare doing kind of a poor man's ECMP or multipass TE with doing multipass TE this way, and say, what's the difference in control plane state and in data plane state? And I think it'll be much more efficient doing MPTE this way. But I mean, tutorialist question, show me a graph, show me how it looks, and prove it to me. So that's the goal. Yeah, thanks for the question. Well, thank you, everyone. Yeah.
Tired.